All right, so this is a talk I would normally give during the year on statistics and science research, but and I would do it live. But with all the stuff being due fairly quickly this year, I figured I would make it taped, and then you guys can pick and choose in this area what applies to you. I'm going to go through different statistical tests, where they apply, and then go through how to run those tests. And at the end, I'll show you how to run it on the computer. You should learn how to do them by hand. That way you understand what they mean. But definitely they all are able to be done by a computer. The big thing is, what does the statistical test, which one's appropriate, and what does it mean, and how do I apply it to my situation? I did give this presentation a couple of years back at National Science Research Teachers Conference, so that's what all this stuff up here is. So it was actually, I worked with a guy called Paul Strode. He's a teacher in Colorado. He's like the guru on this type of stuff. And I learned a lot from him, and definitely very good stuff. This Mathematics and Statistics and Biology is like the book, the resource where you will understand, where it goes through all this stuff I'm going to present today. And I do have this link on the Mass website, shsmri.com. If you just click current students, go down, it'll say stats, and you just need to click there. All this stuff will be there so you can go through it yourself when you're ready to run your statistical test. All right. So just what we're going to be doing here is we're going to talk about why we do statistical analysis, basic review of what it is. Hopefully you've been introduced to it. Hopefully you had ACE Bio. If not, do a little bit of an intro to it. Overview and examples of the four most ones that we're going to use. There are other ones out there. You might see other ones in the literature, but the ones you really will have, I can almost guarantee you, you will be able to use one of these four tests for your research. Chi-squared analysis, linear regression. Most of you will end up using the t-test and the ANOVA. Yeah, we'll look at that real quick. So why is statistical analysis so vital? It is the basics of your research project. Or the basics of a research project are to plan. You have your idea development, background research, your hypothesis, asterisks for a little bit later, methods and paperwork. Then you perform your project, you find a place to work, you order your materials, you run your experiments, you gather data, and finally you analyze. And this, again, where you graph and look for trends, you conclude and you communicate. That step right there, you cannot really conclude or communicate without statistical analysis. It's huge, all right? So we must determine if there is significant evidence to support our hypothesis and reject our null hypothesis, all right? So is there enough evidence to do this? What the heck do those things mean, all right? So only then can we truly communicate the conclusions of our experiment. Statistical analysis gives us the mathematical tools necessary to determine the significance of our data. It is always perfectly fine to accept the null hypothesis. We're going to talk about these in just a second. The null hypothesis is basically when there is no change due to your independent variable or whatever you're doing there. That's totally fine to accept the null hypothesis. If everything went the way we thought it would, we wouldn't need to experiment. And many scientific advances have come from experience that didn't conclude as expected. So it all starts with what we call the statistical hypothesis, which is a little bit different than what you would call your experimental hypothesis. In an experimental hypothesis, we make a specific prediction as to what will happen. For instance, like you would say nitrogen is going to promote plant growth. All right, that would be a hypothesis. If I give a plant more nitrogen, it will grow more or faster. Statistical hypotheses are formulated based on the experimental hypothesis. So statistics are used to test what's called the null hypothesis, and you'll see this represented as H sub 0 or H naught. All right? In most cases, this is where a change in a variable produces no major difference in the experimental outcome. Any differences are just due to chance. This is called the null hypothesis. So there would be no difference in mean heights of the plants with and without nitrogen would be your null hypothesis. No change, even though I added an independent variable in there. All right? The alternative hypothesis, the H sub A, is where the change in the variable does cause a difference in experimental outcome. It does not specify which way, positive or negative, just that there will be an effect. For example, there is a difference in the mean heights of plants with and without nitrogen. You see, your experimental hypothesis, this one up here, the experimental one, may be that nitrogen will make it grow more. Your alternative hypothesis, the one that you use for statistics, will just be like, there is going to be a change. You wouldn't say it would grow more or less, you just say there would be a change. All right? If when we run our statistical tests, we find a significant difference, what we say is that we reject the null hypothesis. We don't accept, and we can accept the alternative hypothesis. So what determines significance? This is something we get to set. It is known as the alpha level. The alpha level is the probability of getting a test statistic rare enough that you're comfortable rejecting the null hypothesis. It is fairly universal in science to set the alpha level to 5%, which is 0.05. So your alpha level will be 0.05 in most cases. When you run your statistical analysis, if the probability value, which we call the p-value, is less than 0.05 or 5%, you can say then confidently that you reject your null hypothesis. Say it again. If the probability value is less than 5%, there is a less than 5% probability that the difference in the results is due to random chance. That means there's a 95%, you're 95% confident, at least, that the difference was caused by your variable. All right? So the keys to success, you probably want to write these down. What we will calculate will be observed value. We observe values. We compare them to critical values found in a table. So these are the things you want to write down. If the observed value is greater than the critical value, which is what you're going to get from the chart, what you'll do is you'll reject the null hypothesis, which means that your independent variable did cause the outcome statistically, and your p-value is less than 0.05. If what you observed, the calculated value, is less than the critical value, you fail to reject the null hypothesis, which basically means that you're accepting it, and therefore, because your p-value is less than, your p-value would be greater than 0.05. That is incorrect. That would be greater than 0.05. All right. Okay. All right, guys, I got it right up there now. So this is the right one on this side, where if the observed is less than the critical, you fail to reject the null hypothesis because your p-value is greater than 0.05. That means there's a greater than 5% chance that it is due to randomness, and thus you have to reject it. Even though it might be, only 6% chance, you still have to reject it. All right. All right, so this is the big one right here. A p-value less than 0.05 means there's a less than 5% that the null hypothesis is true. Thus, the alternative hypothesis is accepted, and there is a difference. And remember, p is the probability that h sub naught, the null hypothesis, is accepted. The means are statistically equal. So basically, your probability that h sub 0 is accepted, if you're looking at it and the difference is there, what you would see there is a lower value of that p would be determine more significance, suggesting that your independent variable did in fact have a change on your dependent variable. The lower that number, the more significant that is. All right, so which tests are available and when should I use them? The next chart is awesome. It should be in, it is online on the MAST website. Please use it. Okay, so if you look at this, you've got this sample flow chart, and he says for statistics using biology, it's all science, all right? So you have to start yourself with what type of data are you looking at? So the first one we look at is this chi-square test. When do you use that? Use it when your data is discrete or categorical. What the heck does that mean? It means you're looking at exact data, something that's descriptive, like I'm looking at color. the color maybe of different plants, or I'm looking at something that's like exact. It's going to be red, or it's going to be green, or it's going to be blue. All right, or a simple value, the exact number of times, the number of times something happens. Okay, that's where you would use the chi-square test. All right. So we're going to look at the chi-square test. We're going to do this really quick. Again, this is explained in that packet, in the packets online. Because the data is exact, so is the prediction. Therefore, when we use a chi-square test, we are determining how the observed results compare to an expected or theoretical result. Usually with this, you're going to have, I expect it to happen exactly like this. I'm going to compare my data to what I expected to happen and see how close they match up. All right. For example, if we flipped a coin 50 times, we would expect there to be how many? 25 heads and 25 tails, right? So our observed result might end up being 21 heads and 29 tails because of randomness, right? How well does that fit the equation, right? The chi-square test compares the expected and observed values with the following parameters for the hypotheses. H sub 0 is that data are consistent with the expected hypothesis, and your alternative hypothesis is that the data are inconsistent with the expected hypothesis. So because we expect the data to match a certain set, and a low p-value suggests a difference between two data sets, in this one, and usually only the chi-squared analysis, a p-value of greater than 0.05 means that you do not reject the null hypothesis. All right. So the observed differences from the expected data likely occurred by chance and are thus not real differences. So this is unique to chi-squared. All right, so enough talking. How do you complete the test? We'll use the coin flip example to illustrate. Step 1, you calculate what's called the chi-squared value using this equation. This value right here, the x squared is the, it's not really an x, it's a chi, a Greek letter chi. Squared is equal to this big guy, which is the sum, the summation, all right, of the observed values. You take each observed value, you subtract the expected value, you divide, and then you square it, then you divide it by the expected value, and then you add every instance of it up. All right? So when you do that, you have your observed, you have your expected, and you only have two of them here. You've got heads and tails. You've only got two different possibilities it could be, unless something landed on its side, but we're not going to put that in there. So you have your observed, so you take 21 minus 25. The O minus E is negative 4, right? 21 minus 25. You square it, it's 16, all right? You divide it by the expected value, which was 25, so 16 over 25, which is 0.64. You do it for the next one, 29 minus 25, which is 4. Again, squared is 16, divided by the expected, which is 25 again, is 0.64. And so you've got those two. You have to add them up because it's the summation of those. So 0.64 plus 0.64 is 1.28. So that's a crazy thing, right? But it's not that difficult. You're going to add those two up, and so if there were, you add those up, and it's 1.28. That's your observed. That's your chi-squared value. All right, 1.28. All right. You then determine the degrees of freedom. For the chi-square test, the degrees of freedom, and it's a term, you're going to need to know statistics, is equal to the number of categories minus 1. Again, this is all explained in the directions for chi-square test, but I'm going over it. So, in equation form, all right, the degrees of freedom for a chi-square test is equal to n minus 1, where n is the amount of categories. So in this case, we have two categories. We're going to subtract 1. There's going to be 1. Basically, the degrees of freedom are the numbers of samples or categories that are free to vary. The 1 is subtracted due to the mean being known. You know the mean of the values. The other values are free to vary. In this case, so 2 minus 1 is 1. So you have 1 degree of freedom. All right? Now you should have all the information you need to go to the table. So there's a table, and it's in the packet. All right. You use the critical values table to determine the probability value, or the p-value, of getting the sum of the chi-squared value, by chance. Basically, the probability that any differences from the expected data are not significant. So in this case, we look at this. All right, we're going to go down here on this side where you have your degrees of freedom. All right, and so that means we have two categories, and we're going to look across here, the probability of distribution occurring by chance. All right, we're going to use the 0.05 as our alpha, as we usually do. So you find your 0.05 and you see where they cross, and it's 3.84. All right, so that value right there, that 3.84, is your chi-squared critical value. If our chi-squared value is less than 3.84, then our p-value will be greater than 0.05, and we cannot reject our null hypothesis. The differences will be due to random chance, and our data matches what we expect. All right. So here's a couple different scenarios on how to do that, blah, 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 and you guys can go through that yourselves. All right. Anywhere where you expect something to happen and want to test the goodness of fit to the model, such as, this is where you would use the chi-square, such as coin flips, something with an expected chance to happen, experimental population curves, genetic testing, does it fit the Punnett square, and so on and so forth. All right, so we need to move on. We're going to move to the next one, which is continuous data. This is, most of your data is probably going to fall into this category, which basically is measured data. It can take on any value within a finite or infinite interval. All right, so you ask a statistical question. Is there a relationship between two variables? All right, does increasing the concentration of this cause a change, cause a linear or nonlinear change in, this is all linear. I'm sorry, we're going to look at linear regression. Does it cause a linear change? Basically, how well does your data fit a line? Does it cause that type of change? So we're going to use what's called a linear regression test. So this is the typical effect of X on Y data. The range of, should be range, not rage, of independent versus dependent variable with an expected trend. And we're going to use the linear regression test. All right, I'm going to move through this fairly quickly. This test will determine if there's a linear statistical relationship between two variables. It is very handy when gathering data that appears as scattered, such as this. Right? So you have this data, you might fit even a linear regression line if you know how to do that, but you want to say, hey, is there an actual trend here? It looks pretty scattered. Is there a trend? All right? So linear regression analysis uses the coefficient of determination, the square of R, or the R-squared test. This is something you probably have seen in Excel when you do this. The R-squared value tells us the strength of the relationship between X and Y and can be interpreted in two equal ways. If your R-squared is 0.94, for example, then you could say that the independent variable predicts the dependent variable Y with a 94% accuracy. You can also say that the pairs of coordinates have 94% of their variance in common. In other words, 94% of the variance in Y values is associated with the variance in X. That just basically means X does cause a linear change in Y with 94% confidence. All right? Let's use that previous singularly scattered data set to illustrate. And there's raw data available in that handout linked on the MAST website. The value is easily calculated in Excel, yeah, so here we go. You can see the R-squared value right up there is 0.052. So plot the data, X versus Y, create the linear trend line, and display the R-squared value. It's an easy way to calculate the R-squared value. There is a long way to do it. Then take the square root of the R-squared value to determine the R value. When you take the square root of 0.052, you get 0.227. All right? So there's your R value. Step 2, determine the degrees of freedom. Again, in this case, there are 2 variables and 10 measurements of each. All right? So you measured, you had 2 variables and 10 measurements of each. So you had your variable A, your variable B, your dependent and independent variable, and 10 measurements of each. So therefore, you had 10 measurements. All right? You're going to subtract, you take your measurements, you subtract your number of variables, and you get your degrees of freedom equal to 8. So you take, in the linear regression, you take your amount of data that you collected. I collected 10 data points. I'm going to subtract the I'm going to subtract the number of variables, which is always going to be 2 for this, and you're going to get 8. All right? So you can see here, number of pairs, the number of data points that you have there, minus 2. And this is going to give you your critical values, which is called R-crit, R-critical, all right, for that, and you're going to use the 0.05 again. Now, in this case, our degrees of freedom was 8, all right, and we're going to use the 0.5 and see where they cross. So in this case, our critical R value is going to be 0.632, all right. If our R value, this is important, if our R value is greater than 0.632, then our P value will be less than 0.05. So what you're looking for here to get a low P value, to get that statistical significance, to say that they do correlate, is you want your R value, the one that you calculated before, the one from the graph, to be greater than the critical R value. And if you remember back, it was 0.2 something. All right, the differences are not, all right, so basically that's what we're looking at here. For this case, our R value, 0.227, is lower than our R critical. Thus, we cannot reject our null hypothesis. There is no significant correlation, which, if you look at that data, that makes sense. I was all over the place, right? All right, so it's like 3 times less than what it should be if it was. Here is an actual calculation of how to do that, and you're welcome to do that yourself, all right? So examples of when to use linear regression, anywhere where you're looking to see there's linear correlation between 2 variables. Concentration of fertilizer versus plant growth rate, age versus blood pressure, population density versus illness rate, and more. Remember, correlation also does not necessarily equal causation. You want to make sure that you remember to limit outside variables, keep as much surrounding the experimental variables as constant as possible, because anything could cause the changes in there, and it might not be what your independent variable was. And so you want to limit every kind of outside factor to only make the only change your independent variable. Okay? Cool. All right, next. Continuous statistical question. Now, a lot of you will be in this arena right here. Is there a difference between the means? All right, so if you only have 2 treatments, all right, if you're only comparing one versus the other, okay, you're taking a bunch of data from column A, a bunch of data from column B, and you're trying to see, is there a difference when I change one variable between the averages of these columns? That would be control group versus one experimental group, and you're running a bunch of tests on each of them. This happens a lot in our field of study, all right? This would be, all right, measurements. So there's 2 types. There's the paired t-test and the unpaired t-test. The paired t-test compares before and after of the samples, the same samples. For example, the comparison of the growth rate of plants before and after adding nitrogen requires its own test. Easily done in Excel, but we're not going to do that here. This is not usually what happens is before and after the same sample. So this would be like, oh, I'm going to take these plants, I'm going to grow them, and then I'm going to add nitrogen and see what happens to them. So yeah, you're going to take a look at the same plants. Usually that's not the case here. Usually we have 2 separate ones. We'd have a plant without nitrogen and a plant with nitrogen, grow them at the same time, and that would be unpaired. All right, so we're going to look at the unpaired t-test. Compares data from different samples. For example, growth rate of a control group plants that do not receive nitrogen and an experimental group that does receive nitrogen. That would be your unpaired t-test. All right, so the student's t-test is used to compare the means of 2 samples to determine whether they're statistically different. If they are statistically different, this allows us to infer that the populations from which the samples were taken were different as well. All right. So let's use the following example. The number of Daphnia eaten by goldfish in 30 minutes in tanks with or without underwater plants. At the end of our experiment, after 10 trials, we get these mean values. Without plants, we got 14.4 Daphnia that were eaten on average, and with plants it was 9.6 Daphnia eaten on average. We did it 10 times in 10 different situations and took the average. Is this difference statistically significant, or is it just due to chance? All right. So Again, we're going to look at H sub 0, the null hypothesis, the means, which would be that the means are statistically equal. Any differences are due to chance. The alternative hypothesis means that the alternative hypothesis is that the means are substantially different. So let's calculate. Step 1 is to calculate the mean of each sample population, each column, and subtract one from the other. Take the absolute value of this difference. I already told you the mean. That's just the average of each column, right? So you subtract one column, the average of one column, minus the average of the other column, take the absolute value. So 9.6 minus 14.4 is equal to negative 4.8. Take the absolute value, it's 4.8. Step 2, calculate the standard error, which you can see the calculation for down here. So you got to calculate the variance first of both samples, all right? So the variance is the S squared value, and that's equal to the sum of each numerical value minus the average squared divided by n, the number of samples, minus 1. You have to do this for every sample, all right? Then divide the variance by the number of measured values in that sample, n, the sample size. Finally, add these two values and take the square root. So you take all of those, and that's a lot. You have to do, this is the biggest step. You take all those and you take the square root. All right? So if you look, we looked at all these, we did the entire thing. You can see all the values here. Boom, 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 add them all up. All right? Divided by n minus 1, the number of samples, which is 10, minus 1 is 9. So 60.4 was the sum of all of them together. So your S1 squared is 6.71, your S2 squared is 5.16. All right, so in this case, you take that. Again, the standard error equation is equal to this value, 6.71, divided by the number of samples. The second one, divided by the number of samples, add them up, take the square root, you get 1.089. All right, then you have to divide the difference between the means by the standard error to give an average value for t. All right, we've calculated both those things already. Compare the calculated value to the approximate critical t value in Table 1, which is on the next page. Table 1 shows the t critical for different degrees of freedom for a significance value of 0.05. The degrees of freedom is calculated by adding the number of data points in the two groups combined, then subtract 2 because you have two means. You have mean from column 1 and mean from column 2. Note that you do not have to do the same number of data points in each group to do the t-test. So that's the cool thing about a t-test. ANOVA, you have to have the same number in each column. In this one, you don't have to. All right. So you can see here the degrees of freedom, the t-critical. In this case, we had... okay, and this is big right here. You want to write this down. If the t observed, the one they calculated, is greater than the t critical, just like in the linear regression, the difference between the means is large enough that you reject the null hypothesis with a probability value of less than 0.05. Rejecting the null hypothesis means that the independent variable caused a change in the dependent variable. If the observed t value is less than the critical t value, you cannot reject it. All right. For example, with the degrees of freedom that we had two columns, 10 in A, 10 in B. We had 20 values. We subtract 2, that's 18. So we're going to use this bad boy up here, 18. All right. Our t-critical value, you can see right there, is 2.10. Our calculated one from earlier was 4.41. Therefore, our observed is greater than our critical, and thus we reject the null hypothesis and conclude that the goldfish ate significantly more Daphnia in the presence of underwater plants than in the presence of plants with a p-value of less than 0.05. That's exactly how you would write that. All right? And that's what that p less than 0.05 means. All right? And there's a practice problem, but we're not going to do that today. All right. Examples of when to use the unpaired t-test. When you need to determine if the means of two samples differ significantly, such as average time to germination of the same species of plants inside and outside a greenhouse, reaction time of students who use training tool versus those that don't, basketball shooting percentage of righties versus lefties, others, so on and so forth. The last one we're going to talk about, and I'm going to go through it super quick, I'm not even going to show you the calculation for it, is the ANOVA. All right, ANOVA is where you talk about more than 2 columns. So you've got, and a lot of you will be using this, you're going to do different variables, but you don't expect like a linear trend, but you want to see different situations. You might be testing different drugs. You might be testing different concentrations of something, but not linearly. It depends, all right? Plants without any nitrogen versus plants with 3 different concentrations of nitrogen would be the ANOVA test. So you're going to have multiple columns of data. You're going to compare them against each other. The one-way ANOVA test is used to compare the means of more than 2 samples to determine whether they're statistically different from the other samples. One-way ANOVA test means one independent variable compared to the dependent. There are two-way ANOVA tests. We're not going to discuss that here. That would be where you have more than one independent variable. It's usually not the case. If that happens, talk to me. We'll figure it out. Like the t-test, if the means are statistically different, this allows us to infer that the populations from which the samples are taken are different as well. So there's an example in here, and you can run through this PowerPoint, and you can see all the calculation I have, but you can see you have multiple columns of data. You have different treatment totals and means and all kinds of stuff like that in there. I'm just going to move through this because I want to get to the end of this, because I imagine you're not going to calculate this by hand right now, although it is really good to calculate this by hand. It's a really good exercise to figure out the difference things that happen with the ANOVA test. All right. So again, you're looking for a p-value less than 0.05. And in this case, you would use the ANOVA test for multiple types of bulletproof vests versus bullet penetration depth. That's one of the projects we had. Mice given various diets versus their mass change. Coral exposed to chemicals versus bleaching rate, so on and so forth. All right. So there's spreadsheet software like in Excel. So if you go to the Excel main page, you can click File, and you select Options at the bottom. Okay. On the left-hand side of the page, click Add-ins, and then go next to the menu button on the bottom that says Manage Excel Add-ins. Okay, so you can get to those add-ins, all right, right there, and click that Go button. All right. From there, you check Analysis Tool Pack and click OK. This is how to calculate all these things, all right? Now click the Data tab at the top of the Data Analysis. For the test discussed here, you can find ANOVA and t-test 2 sample, assuming unequal variances. So chi-squared you probably do by hand. Linear regression you do by hand. But for ANOVA and t-test, you can actually calculate them on the computer. All you have to do is select the columns of data. You just click and drag, and the results are shot out to you. All right. Look for p-values. The alphas should be set to 0.05 automatically. So if the p-value is less than 0.05, your null hypothesis is rejected, and there is a difference in the data. All right. For the t-test, make sure one-tailed is if you're only testing in one direction. For example, that the variable is less than the control on average. Probably not the case in student research, so you would probably want to do the two-tailed p-test. Okay. Two-tailed tests are in both directions. You can go positive or negative. All right. And that's it. All right. That's all I've got time for today. If you have more questions, this was just like basically an overview, and hopefully you guys can skip around and get to what you want. But again, go to the MAS website, go to current students, and go to statistics, and then you'll find all the packets of information on how to do these things there. And hopefully now you know which one to use and when to use it.